Well, in this lesson, I'd like to talk about some common mistakes and misunderstanding of the concept on limit and the limit laws. Okay, especially regarding these four limit laws. Okay, we have a requirement before we can apply these limit laws. And also, before we start, I'd like to start with the first example, which is when x is approaching 0, 1 over x. Does it have a limit? The answer is no. Okay. It doesn't have limit. From the graph, we can see that as x is approaching 0, from larger than 0, let me make the font just a little bit larger so we can see, so we can all see the notation properly. So when x is approaching 0, from larger than 0, it is approaching positive infinity. It is approaching positive infinity. When x is approaching 0, from smaller than 0, okay, it approaches the negative infinity. This theorem, right? If the limit exists, if and only if the limit from left and right both exist, this L refers to a finite number, does not include. But even for that, this observation only establishes that y-axis or x equal to 0 is a vertical asymptote. Okay, it's a vertical asymptote. It doesn't say, and these limits are not a finite number. Okay, if you ask this limit exists or not, the answer is it does not exist. Okay, I hope that is clarified once for all. Okay, so let's look at some other questions that are commonly asked. For example, the first one, the second example, okay, this is the second example. We have a limit 2x over x minus 4, x approaching 4, and this limit is a limit law certainly applied to it. When you see this limit law is applied to it, and your question would be, does the individual limit exist? Because for the limit law to apply, individual limit must exist. So you would check to see, does this limit exist, right? So in order to decide this is true or false, you would like to ask the question, does this apply, right? Does this exist? Does one of it, right? Does both, do both limit this piece and the other piece exist? Do both limit exist? If they don't, you cannot apply limit law. So let's check it, right? Let's check this one first. If one of them does not exist, for example, if x is approaching 4, that means x can approach 4 from either side. So from the graph, we can graph, right? So this is very similar to the 1 over x situation we just discussed. Okay, so that was also the reason we discussed this. So I'm making some adjustment to the picture. So now let's have some adjustment. And obviously, we can establish that x equals to 4 is the vertical asymptote. So we have a vertical asymptote here. So let me draw that picture. You don't need to know how to use the software. So this is a 4. I'm just going to draw this vertical asymptote, broken line. Oops, sorry, I made a mistake. Parentheses, open parentheses. Here we go. Let me adjust it a little bit better. Okay, so you see this picture. Actually, we see this picture. And obviously, when we look at this function, right, when we look at the limit, and depending on if x approaching 4 from left or right, right? So when we observe this limit, we observe the limit from larger than 4, right, which is approaching positive infinity, and or from smaller than 4. Whoops, it's on the shoulder. Okay, that approaches the negative infinity. So apparently this limit does not exist, just like the example we just talked about it earlier. So in fact, the second example, this function is a tweak of 1 over x. Okay, so this does not exist. If this does not exist, and when we apply limit law, both individual limit must exist, and therefore this is false, right? If one of them does not exist, that violates the requirement for applying limit law, and therefore this identity is false. This identity is false, and the reason is because one of the limit does not exist. Okay. However, then you say, well, how do we handle this limit? Oh, certainly we can handle this limit, even though it's not required by this question, right? You just have to operate it. Okay, we have the common denominator, so we subtract 8, numerator subtract numerator, and we can even remove this parentheses, and we factor the top, right? The top was going to be 2 times x minus 4. X approaching 4, but x is not equal to 4, so the limit is going to be 2. So in fact, this left-hand side have a limit, right? So the left-hand side does have a limit in this case, but it's not found by splitting it. In this case, we cannot split it. Okay, so in this case, when we apply limit law, it is a wrong step. This is a wrong step. And for this matter, let's look at the next one. All right, the next one should not be a very difficult fix. Obviously, this quotient rule, the law of quotient is applied here. Can we apply that quotient law, right? Well, quotient law requires that this limit in the denominator should not equal to 0. So this limit, right? Is it equal to 0? If it is equal to 0, then we cannot apply the quotient law. Well, this is a polynomial. We can do direct substitution. And so replace x by 1, Well, this is going to be equal to 0. And therefore, we cannot apply the law of limit on quotient. So this is the easy fix. And therefore, that statement is a false. All right. Now, what can we do, right? So this question is already answered. So when we encounter something like this, what can be done? Well, what can be done is that we cannot, first know, we know what cannot be done, right? We cannot apply the limit law on quotient, but we can still do with it, right? We can still factor this. So if we factor the numerator and denominator, on the top is going to be, if we factor it, it's going to be x plus 7 times x minus 1, I believe. Okay. You guys can mobilize your algebraic, right? So this is x plus 6 times x minus 1, right? After this factoring, then because x is approaching 1, but x is not 1, right? Remember the intuitive definition of limit. X is approaching a number, but is not that number. In fact, if you look at the entire function, x equals to 1 is not in the domain, so x cannot equals 1. But because x cannot equals to 1, x minus 1 is not 0. Therefore, we can reduce that factor. So our next step is that we can reduce this factor, and we ended up with something like this. And that's a rational function, and 1 is in its domain. 1 is in its domain, right? So in fact, we're going to be using this theorem. You can see this theorem is used many times over. Okay, so I'm going to bring these two up. So we're using this ladder theorem over again, and it's a rational function, so we can just do a direct substitution. It's going to be 1 plus 7 over 1 plus 6. So this limit can be found, but not by applying the quotient law. So it's going to be 8 over 7. Okay, so limit law, okay, to apply limit law, we must understand that when we apply the limit law, we have to honor the condition required before limit law can be applied, which is to verify that both individual limit exist, or yeah, so this is very important. So now let's look at the next one. Okay, this one is actually similar to that situation, but quotient law obviously is applied here. So to make sure, well, the top is a polynomial, the bottom is a polynomial. So if the quotient, if the limit of the quotient is not 0, and we can apply the law of the limit. So let's look. So it's a direct substitution because we have a polynomial here. So we just directly substitute, right? So this is going to be 1, and this is going to be 1. And it's not 0, right? Because it's 1 plus 2 minus 4. This is not 0. You don't have to even worry about it is equals to exactly what value. So in this case, yes, this is true. This is true. Okay. And what does it equal to? We can just directly substitute on the bottom, obviously, is we do directly substitute it, right? We can move the whole thing there, right? And the top, we can do direct substitution as well, right? And the denominator is -1. We're almost there. So -2 over -1 and equals to +2. Done. Now, so this example number 4 is true. Number 5, if you look at number 5, the difference between the left and right is that x squared minus 9 is being factored, right? So x squared is being x squared minus 9 is being factored into x plus 3 times x minus 3. So in this case, actually, we just apply this theorem. This theorem would apply here because when x is approaching 3, but x is not 3, by on the limit definition. And we are in the limit setting, so this is true. This is true, okay? Because these two functions are the same except at only one point. So this theorem applies, so this is true. Example number 6. Example number 6 says the numerator has a limit, which is 0. The denominator has a limit, which is also 0. Then the quotient does not exist. This is an interesting question. Okay, this is an interesting question. First of all, we know that is it true or false? First, we know that we cannot apply the law of quotient. We cannot apply the law of quotient for sure. However, does that mean there's no limit? Does that mean there's no limit? We only have to give one counterexample because this statement is very general, right? It's very general. If we have one counterexample, and then this statement will be false. And in fact, we have many counterexamples. I'm going to dig one out from the past, right? We're going to dig one from the past. This one. Okay, we have done the work. We've done the work before, right? So I'm going to copy and paste the whole work. I'm going to bring it here. You can see if we look at f, which is an f, as t approaching 0, the numerator approaching 0, right? So as t approaching 0, the numerator is approaching 0. We can do direct substitution. This is equal to 0. The denominator obviously is also equal to 0, right? So, and this limit for t squared is also a direct substitution equal to 0. So it's a fitting for this condition, but doesn't the quotient have a limit or not? It certainly does. It has a limit in this case. So this statement is wrong because sometimes it is true. So it is not always does not exist. Okay, so this statement is false. Okay, so I'm gonna put a false here. It sometimes is true, sometimes it's false, right? Sometimes it exists, sometimes does not exist. So the statement, the general statement here will be deemed as false, will be judged as false. The next one, okay? So neither one has limit. Does that mean the limit does not exist? Neither one has a limit. Then does it mean the limit does not exist? We actually have a ready example here, which is number 2. Okay, this example. This example, right? In this example, we already demonstrated. We have already demonstrated. Okay, I'm going to bring that work we did here. Right, we did that work right here. Okay. All right. This is F, this is Z. Then you say, hey, this is addition. Oh, that's no problem. We can make it adding -8. Adding -8. And certainly this is false, right? Because we cannot do this. We cannot do this. We cannot do this. But we also know that the individual limit, this limit does not exist, right? And this other limit does not exist either. Okay, we illustrated that this latter limit does not exist. And shall we illustrate this one does not exist? Why not? Let's do that. Right, so this function, if we look at the graph, right, as x approaching 4, I'm making some adjustments to the picture. Okay. So as x approaching 4, we certainly don't have a limit. I'm just going to make it a little bit easier for us to observe. Just 1 second. Okay. And the horizontal, and there's a vertical asymptote. There's a vertical asymptote. The vertical asymptote is okay, I'm making red, broken there. So there's a vertical asymptote. So this also tells us that this piece, the function, does not have limit as x approaching 4. Because when x approaching 4, from positive direction, it goes to positive infinity, otherwise it goes to negative infinity. So both limit does not exist. But both limit does not exist only illustrate that we cannot apply the limit law. We cannot apply limit law. It does not mean the initial limit does not exist, right? So this does not exist as a false statement because we have demonstrated, right? However, we have shown this limit doesn't exist. Therefore, this statement is false. The statement is false. Okay. So let me gonna put it together. So this statement is false. So I hope that this clip explained to you what can be done, what cannot be done, right? So when we apply limit law, we have to honor the requirement for the limit law application. If the limit law application conditions are not satisfied, we cannot apply limit law. That's all. Thank you for watching.